Potentiality of using Cissus Populnea stem fiber as reinforcement for cement fiber board produced from waste paper. Abstract: this research work studied the utilization of a renewable, non-hazardous fiber processed from Cissus Populnea plant and pulp fiber obtained from recycled waste paper for production of low-cost, medium-density boards suitable for ceiling and walling applications. Cissus fibers were mixed at 4 different percentage level of 0, 2, 4, 6, and 8% by weight of cement with a constant mass of pulp fiber and cement to form a total matrix composition of Cissus fiber, pulp fiber and cement. The mixture was compressed in a square mold of dimension 150 mm x 150 mm x 20 mm at a pressure of 5 bar to produce a medium density boards of volume 150 x 150 x 10 mm3. A total boards of 36 samples were produced and subjected to impact energy, water absorption, thickness swelling, density and thermal conductivity tests. The impact energy of the board ranged between 3.08 and 3.98 J, water absorption of 0.24 and 0.30%, thickness swelling of 0.52 and 0.90%, density of 670 kg/m3 to 735 kg/m3 and thermal conductivity of 0.075 W/m.K and 0.092 W/m.K. The results of the properties tested showed a moderate relative standard values as compared to commercial fiber ceiling boards. The use of Cissus fiber will eliminate energy consumption involved in the processing of synthetic fibers and also reduce the present and future environmental hazard that synthetic fiber-based composites could cause to human health. Keywords: Cissus fiber, synthetic fiber, sorption properties, impact energy, thermal conductivity. 1. Introduction. In recent research developments about the importance of synthetic and natural lignocellulose fibers as a versatile material for reinforcement in the production of fiber-reinforced composites, FRC. Plain non-reinforced cementitious materials suffered low tensile strength, they are brittle and require reinforcement before they can be used as construction materials when subjected to tensile loading. Meanwhile, scholars have revealed that there is high energy consumption and environmental health hazards constituted when synthetic fibers such as asbestos, polyethylene, glass, carbon fiber etc. are processed for their utilization as reinforcement materials in the production of fiber-reinforced composites, FRC, that are widely used for building construction. Even some of the manufactured end products from synthetic fiber has been proved to constitute health hazard when in service. Example is asbestosis caused by inhaling asbestos ceiling board particles. As a result of this challenge, attention has now been shifted to utilization of renewable natural lignocellulose biofibers. These fibers are renewable, non-hazardous, environmental friendly, and easy to handle during processing. They have inherent physical and mechanical properties such as toughness, high strength-to-weight ratio and high tensile strength that make them useful in the production of fiber-reinforced composites, which could also alleviate the problems of high price among contemporary building materials such as corrugated aluminum, asbestos cement board and galvanized roofing sheets. Fiber control multiple cracking and reduce deformation at all stress level, thus imparting post-yield and post-cracking behavior, fracture toughness, ductility. Thus energy absorption capacity of the composite are then substantially improved. Olaoye et al., 2009. Sisal, bagasse, banana fibers have been experimented by some authors as reinforcement materials in the manufacturing of FRC, and the results of their findings on the various properties tested fall in line with the engineering standard parameters that are usually considered before FRC can be recommended for some specific applications. This development has also assisted in production of low-cost building materials using natural fibers and recyclable wood-based waste fibrous materials such as waste paper. Waste paper are generated daily in tons. It can be recycled and converted into another useful products, otherwise use as a secondary fiber, which can also serve as a filler material in FRC production. More frequent use of waste paper in FRC production may likely prevent the present and future menace that the enormous waste paper generated could have caused. Therefore, This research work focused on utilizing pulp fiber from waste paper and natural lignocelluloses Cissus Populnea plant fiber for the production of medium-density fiber-reinforced cement board, hence, exploring its suitability for ceiling or side walling applications. Cissus Populnea is a high fibrous plant, Table 1.0, having unique characteristic of high crude gum composition of 38.3 plus or minus 1.9, 40.4 plus or minus 3.5 g/100 g on dry basis, Olaoye et al., 2012. It is widely known for its mucilage, gum, consumption and numerous medicinal values, but no record of its utilization as fibrous material. 2.0 Materials and methods. 2.1 Sample collection and preparation. Locally sourced fresh Cissus Populnea stems of about 10 cm long and 90% moisture content were manually depithed and oven dried to a constant mass. The fibers were removed and cut into length of 20-30 mm suitable for reinforcement. A bag of Portland cement, Elephant brand, procured for the production of the boards was stored in a tight sealed container to avoid moisture absorption before use, and the waste papers that were recycled into pulp were obtained from spent office papers in Federal College Forestry, Ibadan, Oyo State, Nigeria. The papers were soaked in water for 3 days, digested by using a disintegrator, and finally drained before oven drying to a constant mass. The matrix for the production of the boards was shown in Table 2.0. Each proportion was mixed to form a slurry before pouring into wooden mold of 150 mm x 150 mm x 20 mm placed on polythene nylon. The surface of the mold was also covered with polythene nylon before the cold pressing to enhance the surface smoothness of the board surface. Thereafter, the mold was vibrated using motorized vibrator to allow uniform distribution of the slurry across the entire surface area of the mold. Hydraulic cold press machine rated 25 bar maximum pressure was used to compress the boards. Proposed sample thickness of 10 mm was obtained at a pressing pressure of 5 bar, and this pressure was constantly maintained and left for 2-4 HRS before demolding. All samples were cured in water for 1-2 HRS and air dried for 2-4 HRS under room temperature of 21-270 C before they were subjected to impact energy, water absorption, thickness swelling, thermal conductivity and density tests. 2.2 Physical properties test. The samples were prepared in accordance with standards for testing materials, ASTM D743-13, 2013. The final size of each test sample was 150 mm x 100 mm x 10 mm, and 36 samples were tested for the selected properties. 2.2.1 Water absorption and thickness swelling, immersion method. Initial weight of test samples at room temperature of 250 C 270 C were determined prior to horizontal submerged of the samples in water. The samples were removed from water after 2-4 HRS and allowed to drain before final weights were taken. The water absorption and thickness swelling of the samples were computed using equation 4 and 5. 2.2.2 Density. The mass of each sample was determined using sensitive weighing scale of 5 kg maximum weighing capacity, and the densities of the samples were determined using equation 6. Density equals dash 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 6. M equals mass of the sample, kg. V equals volume of sample, m3. 2.3 Impact energy test, free fall method. A sample was suspended on two ends support of span 100 m placed at the base of calibrated impact energy testing equipment, and a steel ball of known mass was allowed to drop freely on the sample from a recorded least vertical height. The initial height from where the ball falls was gradually increased until failure, cracking, of the sample occurred. The final height at which failure occurred was recorded, and the impact energy was computed in joule, J, using equation 3. E equals mgh, 3. M equals mass of steel ball, kg. G equals acceleration due to gravity m/s2. H equals height of the fall at which sample failure occurred, m. E equals impact energy, J. 2.4 Thermal conductivity test, non-steady state method. Thermal conductivity test was carried out using digital KD2 Pro Thermal Properties Analyzer, KD2 Pro Utility. The probe of the equipment was directly inserted into each sample and the value of the thermal conductivity displayed on the KD2 meter screen was recorded for evaluation. 2.5 Statistical analysis. Data obtained were subjected to descriptive statistics, analysis of variance, ANOVA, and line graph. 3.0 Results and discussion. 3.1 Results. Table 3.0 Computed mean values of the properties of Cissus Populnea stem fiber and pulp fiber reinforced cement boards. Mass of fiber, G. Mass of dry pulp fiber. Mass of cement, G. Total weight of composite matrix, G. Impact energy, J. Water absorption, %. Thickness swelling, %. Density. Thermal conductivity, W/m.K. Discussion. Thickness swelling and water absorption values range between 0.52%, 0.90% and 0.24%, 0.30% respectively. The highest values of water absorption, 0.90% and thickness swelling, 0.30%, were obtained at maximum Cissus fiber reinforcement of 8%. This implies that, increasing the fiber percentage in the board will increase the board affinity for water absorption. This increased rate for water absorption and thickness swelling may have occurred due to hygroscopic nature of lignocellulose fibers which allow for moisture intake. The trend obtained in this result correlate with Olaoye, 2009. Density of the boards is a function of fiber-cement ratio. It ranged between 670 kg/m3 and 735 kg/m3. The density increases with increased Cissus fiber. The pulp fiber in the matrix which serve as both reinforcement and filler material control the density of the boards within acceptable range of 500 kg/m3 800 kg/m3 for medium density fiber board. The polynomial rank correlation, R2 equals 0.78 between density and impact energy of the boards as depicted in Fig 6 indicate that the impact energy of the board is also a function of density of the boards. The impact energy obtained from the free fall method is the energy required to cause the failure of the board when subjected to impact loading. It can also be interpreted as the maximum impact loading beyond which failure will occur. The values ranged between 3.08 J and 3.98 J. It is maximum at 8% Cissus fiber reinforcement. The energy increased between 0% and 6% and reduces between 6% and 8% fiber reinforcement. This trend showed that, increasing the reinforcement of the composite above 8% fiber reduces the impact energy of the board and will therefore affect its ability to withstand more impact loading. This behavior can also be traceable to excess fiber to cement ratio of the composite board. The same findings was reported on natural sponge fiber reinforced cement boards by Olaoye, 2009. Comparing the values obtained to the findings of Akinbosoye et al. 2015 on the mechanical properties of waste paper sealing board, it was observed that, the use of Cissus fiber as additional reinforcement material is a factor that increase the impact energy values of the boards. The thermal conductivity of the composite board determined heat conductivity potential of the board with respect to time and change in temperature when used as ceiling or wall siding material for construction. It ranged between 0.075 W/m.K and 0.092 W/m.K. The maximum thermal conductivity of 0.092 W/m.K was obtained at Cissus fiber reinforcement of 4% while the least 0.075 W/m.K was obtained 8%. It was observed that increasing Cissus fiber above 4% reduces the thermal conductivity of the boards, which is attributed to high interlock bonding spaces between the Cissus fiber and cement. The thermal behavior of this board correlate with the result of the thermal conductivity of the board produced from rice husk and waste paper by Akinbosoye, 2016. Conclusions and recommendation. The results obtained from the study showed that, using Cissus fiber as reinforcement materials for production of medium density board for ceiling and walling applications, This will eliminate energy consumption and environmental hazard caused by synthetic fibers. The range values of the board impact energy, thermal conductivity, water absorption, and thickness swelling fall within the standard values that will make the boards acceptable for use as light load-bearing member for construction. The use of Cissus fiber alone or in combination with other lignocellulose fiber as reinforcement material and extension to production of fiber-based composites for other applications such as roofing and flooring is hereby recommended.